Right, here we're going to prove that the sum of the squares of the lengths of a parallelogram's diagonals is equal to the sum of the squares of the lengths of the sides, and we're going to use vector methods for that. Now that's a real mouthful, but what we're saying is if I add the square of the length, so the magnitude of AC and DB to each other, they will be equal to the sum of the squares of the lengths of all of the sides. Okay, so I've been given that ABCD is a parallelogram. Okay, and the importance of that is that I know that the properties of a parallelogram include two equal and opposite parallel sides, and I'm going to use that to help me to do my proof. So what we need to prove is that the magnitude of AC squared plus the magnitude of DB squared is equal to the magnitude of AD squared plus the magnitude of DC squared plus the magnitude of CB squared plus the magnitude of BA squared. So that's all of my sides. For ease of use, I'm just going to make AD equal A and DC equal D. So let's let A, D be A, and I'm going to let DC be D. And I can say, okay, let's have our proof going here. Since ABCD is a parallelogram, I know that AD is equal to BC, which is equal to A, and I know that DC is equal to AB, which is also equal to my vector D. Now if I do my sum of my square of my sides, so let's do that, sum of my square of my sides, well, what I've got there is I've got the absolute value of AD squared plus the absolute value of DC squared, or the magnitude, plus the magnitude of AB squared and the magnitude of BC squared. Now I've called them A and B, so I can actually make that a whole lot easier. It'll be the magnitude of A squared plus the magnitude of D squared plus another A squared plus another D squared. And that works out to 2 times the magnitude of A squared plus 2 times the magnitude of D squared. Okay, so I've summed my sides. Now I need to figure out how to relate that to the diagonals. Okay, now if I have a look at my diagonal DB, if I want to go from D to B, I'm going to go minus AD, or DA, plus AB, or I'm going to go from D to C and then C to B. Either way around, okay. I'm going to do it here on the right hand side so we can see. So now vector DB is going to be DC plus CB, and we know that DC is going to be D and CB is negative A, all right? And I can also see that AC is going to be AB plus BC. And that's going to be D plus A, okay? Now if I want to sum the square of my diagonals, okay, so sum of your square of your diagonals, that's going to be the absolute value of dB squared plus the absolute value of AC squared, and that's going to be D minus A plus D plus A squared. And I know that when I square vectors, I can write that as D minus A plus D plus A, D plus A, and I can use FOIL to expand, okay? And remember, just make yourself a note, remember that A dot A is the same as the absolute value or the magnitude of A squared, and that's why we can find the dot product over here. Okay, so using FOIL and our dot product, we've got that D dot D minus D dot A minus D dot A plus A dot A plus D dot D plus D dot A plus D dot A plus A dot A. So I've expanded it, okay? And when I simplify through there, I get 2 times D dot D plus 2 times A dot A. And remembering that A dot A and D dot D gives me my absolute value or my magnitude squared, that's equal to 2 times my absolute value of D squared plus 2 times my absolute value of A squared, which is the same as what I got over here when I summed my my sides. All right, so I can say, therefore, AC squared plus DB squared is equal to AD squared plus DC squared plus AB squared plus BC squared, and therefore the sum of the squares of the diagonal lengths equal the sum of the squares of the side lengths of a parallelogram. I can't fit that in.